right, so we are now into the last unit of pre-calc, which is the introduction to calculus. And this first section is all about limits. And this is actually going to be the entire set of notes, so it's going to be quite, well, I mean, you guys have the actual printouts of them. I'm going to go through all these notes. You know, if you don't have time to listen to all this now, you can do it in chunks because I'm not going to do notes every day this week, just this one, and then we won't do notes again until Thursday. All right, so estimating limits graphically, first off, this is a slight review from Unit 1. When we talked about end behavior, we did use limit notation on that. So if we remember for limits, we would say that we have the limit as x approaches, and our end behavior was approaching infinity, and we're taking the limit of the function, and that's what we're trying to determine. So our end behavior, this is in limit notation. So as x approaches infinity, so as the x values are getting bigger and bigger and bigger, the y values are also getting bigger and bigger and bigger. So the limit as x approaches infinity would also be infinity. That would be the right end behavior, and then our left end behavior, so as x approaches negative infinity, so as our x values are getting over here, so as our x values are getting big or smaller and smaller and smaller, our y values are also continuing to get smaller as well. So our end behavior would be negative infinity. All right, so if you want to give this one a go, I'll just write down my limit notations here. So in this case, our right end behavior, as the x's are getting bigger, my y values are headed down towards 0. So my end behavior on this one is 0. And the same thing for the left side. As my x's are getting smaller, the left side, my y value, it's still approaching 0. It does cross over that, but it does maintain a closeness to 0. All right, and that's pretty much what limits are. It's just about what is the graph approaching at that particular value. Now, there are 3 types of discontinuity, if we remember from those. Can you name those? Okay, so we have those 3 different types of discontinuity. Anyone? 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 All right, so our 3 types were infinite, removable, and lastly, jump. So those are our 3 different types of discontinuities. So infinite discontinuity, an example of that, well, if it's an infinite discontinuity, it has at an x equals c value, the function will increase or decrease indefinitely as x approaches c from the left and the right. So just an example of that. So what that means is, if, you know, just in general, just saying that, hey, this is a c value, okay, so just a general c value. So as you're approaching this value from the left side and from the right side, if they are increasing or decreasing indefinitely, then it is an infinite discontinuity. Okay, so basically it's approaching an asymptote. A removable is where it's continuous except at x equals c. So the removable, that was also a whole. So once again, just in general, if you have a value, an x value, in this case c, and our graph is continuous, except, oh, right there, we do have a hole right there, and then it continues on from that point. So that would be a removable discontinuity. And then lastly was the jump discontinuity. So a jump discontinuity means that the limit from the left side and the limit from the right side have 2 distinct values. So a jump discontinuity would look like something like this. So as you're coming from the left, approaching this c value, in this case negative c value, approaching this c value, as we're getting closer to that c value, the y values are very different. So coming from the right, coming from the left, our y values are approaching different values, and that's what a jump discontinuity is. Okay, so from infinite geometric series, there's some sense of limits that we could give limit a conceptual description. Okay, so a limit is intended function value at a given x. Whether or not the function actually reaches that value, that is not necessarily what a limit is. A limit doesn't it's not what the value actually is. It's all about what it is approaching from the left and the right side. So what that means is as you're following, here's our C value. So as you're approaching this C value from the left side and you're approaching that C value from the right side, they are coming together at a particular value, in this case L, at a particular Y value. So what is it approaching from the left? What's it approaching to the right? That is what a limit is. Now, sometimes you don't have an actual value. For instance, a removable discontinuity has a limit, but it may not have a value. So in this case, I'm just going to change this to, say, we'll just make it a number. So if that's a 4. All right, so as I'm approaching that 4 from the left and from the right, from the left side as we're approaching 4, the Y values are headed to 1. From the right side as we're approaching 4, the Y values are headed to 1. So the limit is 1. However, there may not be an actual value. So you may not have an f of 4 value. That doesn't exist because there's a hole there, but it does have a limit. So the limit as x approaches 4 of the function would be 1 because it is coming from the left and to the right side. That's what the definition of a limit is. All right, so how do we estimate limits? Well, numerically, we're just going to be able to take and look at a table. That's what that means. So you're just going to plug your function into your calculator, and then you're looking from the left and from the right to see what your values are actually approaching. Okay, so for example, I'm just going to do a linear function. So if you're using a table, literally you're just, we'll just do 8x plus 2, just making something up. And then we're looking at, I guess I need to write down what the limit would be. So let me go back to that really quick. Okay, so if we have the function f of x equals 8x plus 2, and I want to know the limit of the function as x approaches 4, what would that be? So if we're using a table to find the limit for this, what that means is we're going to do is we have a 8x plus 2 in the table. Whoops, hit the graph. Okay, so in the table, try that again. What we're trying to do is figure out what the limit as x approaches infinity, or 4 would be. So what that means is as you're coming from the left to 4 and as you're going to the right of 4, what y value is it approaching? Now, this one actually has a value, which this is also the limit. So the limit would be 34. Because as you're getting closer and closer to 4, the y value gets closer and closer to 34. That's pretty straightforward. All right, so the other way is to take a look at the actual graph of it. Oop, wrong one. There we go. Okay, so graphically, you can use your calculator or sketch it by hand. Again, just looking at the actual picture and determining what the y value is, or when the x value is approaching a particular value, what y value is it headed towards. Calculator. All right, and then the last one would be analytically. This means algebraically, which that's the next section. Algebraic. Not spelling that correctly. Did I spell? Yeah, I misspelled that. There we go. Yeah, it looks terrible. All right, anyway, so algebraically. Okay, so we have what are called one-sided limits. So one-sided limits look like this. So you'd have the limit of f of x as x approaches c, and then you have this little negative up here. Okay, so what that means when you see this, and that would be equal to, say, an 11, or say L. So what this means, the way you would read this is it says the limit of f of x as x approaches c from the left is L. That's how you would read that. Limit of f of x as x approaches c from the left is L. And then we would do the opposite to show from the right. So the limit of f of x as x approaches c, and then there's a little plus here. That means from the right, so is L. I'm going to be lazy. The limit of f of x as x approaches c from the right is L. All right, so let's take a look at some graphs for this. Okay, so the limit of f of x as x approaches 1 from the left. Okay, so we're looking at the x value of 1. Here's the x value of 1. Okay, and what we're doing is we're coming from the left side headed towards that 1. So as you're coming from the left, where is the y value headed towards? Well, the y value is headed towards -1. That's the limit as it's approaching f or 1 from the left. Okay, well, what if I'm approaching it from now the right? It's going to be different in this problem. So as I'm approaching it from the right side, okay, right, coming from the right side, I'm just following the graph. As I'm coming from the right and I'm headed towards the 1, my limit is now 0. All right, so there's my y value of 0. And that's how that works. All right, so as x approaches 2 from the right. So let me get rid of some of these things here. All right, so I'm approaching 2. Here's 2. I'm approaching it from the right side. That limit is going to be 1. As I'm approaching 3 from the right. All right, so here's my 3. As I'm coming from the right side, my limit is 1. 0 from the left. Whoop, thought I hit my eraser. There we go. All right, okay, here's 0. As I'm coming from the left side, what is the y value headed towards? The y value is headed towards 2. As I'm coming from the right side, so I have all this, whoop, whoop, here it comes as I'm getting closer and closer to 2 from the right. It is also headed towards 2, so that limit is 2. Okay, so once again, for a limit to exist, an overall limit, the left and the right side limits have to be the same. Okay, so for instance, if there's not a designation, okay, so a designation left side or right side, if there's not a little designation over there, that is just an overall limit as x approaches -8. And what that means is that your left and your right end behavior, or excuse me, your left and your right limits have to be the same value in order for this overall limit to exist. All right, so f of -8, that's an actual value. That's actually telling me what is the y value when the x is -8. So when the x is -8, here's my x -8. Okay, I do have a hole here. This is the actual value of it. That is -3. Okay, now the limit is different. The limit of -8. So when I'm approaching -8 though, it's not going to be -3. Again, it's not about what it's equal to, it's about what it's approaching. So as you're coming from the left and from the right, the y value it's approaching is -6, even though the actual value of -8 is -3. Okay, so I'm going to jump up here to these 6's over here. I take that back. Okay, so you have -2 from the right, or excuse me, from the left side. Let me get rid of some of these colors here. So -2 from the left. So here is -2. I'm coming from the left side, and it's approaching the y value of 3. All right, 10. As I'm coming from, here's 10. There's no designation, so that means that from the left and from the right have to go to the same value. So as I'm coming from the left and from the right side, those are both headed towards the y value of 0. Okay, so number 6 here. F of 6. We want to find the actual value. So when I'm looking at 6, okay, so here's the x value of 6. So the actual value of 6 is, well, there's a hole here. So the actual value of 6 is 5. So f of 6 is equal to the y value of 5. So the limit as x approaches 6 from the left, so I'm coming from the left side, I got all this over here from the left, my y value is approaching 2. But as I'm coming from the right, my y value is approaching 5. because the left and the right end limits are different, the limit as x approaches 6 does not exist. The left and the right have to be the same answer for the limit to be, for you to have an overall limit. All right. Okay, so again, that's what I'm just saying here. So note that the limit of f of x as x approaches c is equal to L if and only if the limit as x approaches c from the left is equal to L and the limit of f of x as x approaches c from the right is also equal to L. If these two are the same, then the overall limit will exist. All right, some things that do not exist or limits that fail to exist. Again, what I just said, if the left and the right are different, it does not exist. So here's an example of that. So the limit as x approaches -4, from the left is 6, but from the right it's 3, therefore it does not exist. It increases and decreases without bound as x approaches c. What that means is that as you're approaching 0, the function of this 1 over x looks like this. So from the left is going to -infinity, but from the right it goes to +infinity. So therefore it does not exist because they're headed in two different directions. And then lastly, if f of x oscillates between two fixed values as x approaches c, so the example would be this function here, limit of sine of 1 over x as x approaches 0. You could take a look at the calculator. It's kind of let's see here. So we got, so I'm not going to be able to draw it justice. So we got sine of 1 over x. Let me make sure I'm in radians here. Nope, not. Okay. Okay, so what's happening as it's approaching 0? If you zoom in on this, it's like a big EKG graph or something. So it's oscillating, it's bouncing back and forth between two values right there. So it does not exist because as it's just going, basically it's going haywire in between there. All right, so those are types that do not exist. Okay, so here's again just another practice of limits. If you want to just pause it for a moment and then check your answers, because these are very quick problems. We can go from there. So, all right, so just you try them really fast and then come back and then check your answers. All right, so limit of the function as x approaches infinity. So as your x values are getting getting bigger and bigger and bigger, what is the y value headed towards? All right, to me, because this is counting by 2's, to me this is headed towards 1. So the limit of g of x approaches -6 from the left side. So as you're approaching it from the left, coming from the left, here's -6 coming from the left, the y values are headed towards infinity. As you're approaching 6 from the right, well, as you're approaching 6 from the right, okay, it's coming from the right side, so approaching -6 from the right side, that's headed towards -infinity. So you know what that means? This guy right here does not exist because these two limits are not the same. All right, so -infinity. So as you're approaching -infinity, as your x values are getting smaller, the y values are also headed towards 1. And then as you're approaching 4. So 4 from the left is going to infinity, from the right goes to infinity, therefore they're headed in the same direction, so it's going to be infinity. Okay, so now what you're going to do is just use your calculator to find the limits of these. So you could just take a look at the graph, or you may want to look at the table of it. All right, so let me pull up my calculator here. Okay, so we have the function that was x plus 6 divided by x minus 2. And we're approaching x as x approaches 2. So if I look at my table, I'm going to do a little table setup here. I'm going to start it at 2, but I'm going to count by tenths. And now when I look at the table of this, we can see that as I'm coming from the left side, as I'm coming from the left side, these are getting definitely smaller values. They're headed towards negative numbers, whereas I'm coming from the right side, they're headed to bigger positive numbers. So they are headed in different directions. Now, once again, even though you do not have an actual value at 2, that doesn't mean that you don't necessarily have a limit. Again, it's not about what the actual value is equal to, it's about what it's approaching. Okay, it may look a little bit more sense when we take a look at the graph of this. So as we're approaching 2, 2 going from the left is going to negative numbers, 2 coming from the right is going to positive numbers. Therefore, it does not exist because they are not headed in the same direction from the left side and the right side. So this one does not exist. All right, the limit of this function as x approaches infinity. Again, probably want to take a look at that graph. I'll do a couple more where I'm looking at the graph of it. All right, so I have a negative 3x to the third plus 6 divided by 4x squared plus 2x plus 7. All right, and either taking a look at the graph or the table. Make sure I type that in right. Negative 3x to the 4x squared plus 2. Okay. Okay, so as x is approaching negative infinity, so as the x values are getting smaller and smaller and smaller, we can kind of tell that the y values are going towards negative infinity also, or as the x values are getting bigger and bigger and bigger, the y values are getting smaller and smaller and smaller. Take a look at the table of it. In my table setup, I'm just going to now count by, I don't know, tens. Okay, so as you can see what's happening, as the x values are getting bigger, my y values are definitely getting smaller. It's not headed to any particular number, it's just headed towards negative infinity. So that guy is negative infinity. Okay, just because I don't want to have you guys suffer through me typing all of these into the calculator, I'm just going to tell you what the answers are with these. But I would give these a try on your own, and then, so maybe pause it right here, try those answers, and then check your answers accordingly. Okay, so letter C should not exist. Letter D, as x is approaching infinity. So this is a piecewise function. So as you're coming, so as the x's are less than 0, so as you're coming from the left, remember we can plug 0 in. This limit would actually be a negative 5. It's going to approach negative 5. When I plug this in, this would be 3. So from the left and from the right, it's different. So this does not exist. As x approaches 4, this one should be 9. And then as x approaches infinity, should be negative 3. If you do have questions, please email me, and then we can go through anything that you want to go through on that. But hopefully you got the, hopefully you got those correct. Okay, so that's negative 3. Alrighty. Okay, so continuous. Basically, continuous means there's no breaks in the graph. There's no hole, there's no jump discontinuity, it doesn't approach infinity. So it's going to be continuous if the left limit, so as the limit of f of x approaches c from the left is equal to L, the right limit, c from the right, approaches L, and then if the actual value is L, then it's continuous. So is the graph continuous? Again, it is pretty straightforward. It's no breaks in the graph. So is the function continuous at x equals negative 1? Okay, so as x equals negative 1, if we went through our little checkpoints here, so the limit as x approaches negative 1 from the left is 3. The limit as x approaches negative 1 from the right is, we'll just go with 1. It's a little bit less. But the actual value of it is 3. These three things have to be all the same answer for it to be continuous. So this one is not continuous. But we can see that, guys, right? Look, there's a gap right there. So it's not continuous. Is it continuous at 1? Well, if I'm approaching 1 from the left, it goes to infinity. 1 from the right, it goes to 3. The value of 1 does not exist. So no, this is not continuous. is it continuous at 2? So as I'm approaching 2 from the left, 2 from the right, the actual value of f of 2 is all the same. It's all about 3.5. So this one, yes, it does exist. Okay, so the limit of -1. So as you're approaching -1, once again, this does not have a limit because the left and the right are different. Now it approaches 1. So as you're approaching 1 from the left and from the right, it does go to 1. 2 from the left and to the right, and the actual value of that is about 3.5. Okay, and then the last little bit here is just to try and sketch a function that has these characteristics. And there is definitely more than one answer for this. If you're not 100% sure on yours, you can take a picture of it and email it to me, and I can tell you if you've met the following characteristics. But once again, you can pause it, try to draw these, and then make sure, again, if you want me to check them, you can send them over to me. I'll just show you some examples. All right, so we have a removable discontinuity at x equals 2, non-removable discontinuities at 3 and -3, x-intercepts at -1 and 5, and a y-intercept of 2. All righty, let's see here. So a removable discontinuity at x equals 2. Okay, so that means there's basically going to be a hole there. Non-removable discontinuities at 3 and -3, so that means that they are either an infinite or a jump discontinuity at that point, non-removable. And x-intercepts at -1 and 5. Okay, so I know I need that to cross here. That's 2, 3, 4, 5. I know I'm going to have an x-intercept there. And a y-intercept of 2. Got something up there. Okay, so at x equals 3 and -3. Okay, I'm just going to make 2 asymptotes at 3 and -3. I have a hole there, and then maybe it comes back up here. And then this guy, and maybe you have some over here. All right, so there's something that would work for that. Has all those values. And then lastly, we'll do this next sketch here. Continuous at x equals 3. The limit of x of f of x as x approaches -1 is 4. F of -1 is undefined. Limit of f of x. Okay, all right, so I'm just going to pause it and draw because I feel weird talking through my drawing. Okay, so here's what I came up with. It's continuous at 3. So what that means if it's continuous at 3 is that the limit from the left, limit from the right, and f of 3 are all the same value, which they are. The limit of f of x as x approaches -1. So from the left and from the right, the limit is 4 as I'm approaching -1. However, -1 is undefined, so that means there's a hole there. Once again, limits are about what it's approaching, not what the actual value is. Limit of f of x does not exist at x equals 5 or x approaches 5. So as you're approaching 5 from the left and from the right are different values, so that limit does not exist. And lastly, the limit of f of x as x approaches -infinity is at 0. So as my x values are getting smaller and smaller and smaller, the y values are coming down here towards 0. Okay, so again, there are a million different ways that you could have drawn this. This is just a couple of ways that I came up with. All right, so for now, we are in the works of talking about trying to set up Delta Math. So that'll probably be sent out to you tomorrow. And then, like I said, these are really long notes for today, so you're not getting any more new notes. So yeah, this is about 30 minutes long. So, it was Monday, Tuesday, Wednesday stuff that you are getting done. I hope that made sense. All righty, guys. Have a good day.